Well, so let us solve a question from GATE 2018. That question number is 41, and this is basically from nuclear physics. So that question is given that you have a fluorine nucleus having mass number 19, and obviously you have proton number or atomic number that will be 9. Okay, and you have a state that is on the 3/2 and on the 5/2. Okay, the state cell structure of nucleus according to the cell model, and you know that d5/2 that will be lower state as compared to d3/2, and the protons are filling. So when there is a de-excitation of proton from on d3/2 to on d5/2, this is the upper state and this is the lower state. Okay, so if you see that spin orbit coupling in cell model, the state having a higher J with same L will be lying in lower state. And you have a fluorine nucleus, you can see here that proton is unpaired. So last proton will be unpaired, and this proton is at excited state according to the given in the question. When this proton is making de-excitation from this higher state to lower state, there is an emission of photon or gamma ray having energy that is given 4 mega electron volt. Okay, so you have this nucleus and these are the state. Proton from higher state d3/2, when it is de-exciting to d5/2, there's an emission of gamma ray having energy that is provided. And also it is given that spin orbit contribution in the total energy, that energy is provided. That is C expectation value of L dot x. So this is the spin orbit contribution in the total energy. Now you have to find that C value that you have to calculate in terms of mega electron volt, that you have to calculate. Okay, so as you know, if you this is the spin orbit contribution in that energy, so total energy of the system, that will be some unperturbed energy, and you will have spin orbit energy. And you have two state here having same L value, and so basically E0 will be same. So their energy difference is coming because of this spin orbit energy, and both having different spin orbit energy. So let us calculate that spin orbit energy of nucleus. So you can calculate this spin orbit energy. So as you know that J equals to what? L plus S. J equals to L plus S. Now if you take J dot J, that will be L plus S dot L plus S. And that will provide you J dot J, that is nothing but J square, equals to, here you will have L dot L, that will be L square, and then S dot S, that will be S square, and you will have L dot S plus S dot L. So L dot S and S dot L. So you can write S dot L, that is nothing but L dot S, and you have another L dot S, that will provide you 2 times L dot S. And from here you will obtain that L dot S. L dot S, that will be nothing but J square minus L square minus S square. Right? So it means basically L dot S, that will be expectation value of J square, that is nothing but J into J plus 1 minus L square ka L into L plus 1 minus S square, means you cannot see here, I'll write here. So we'll have expectation value of L dot S. It means you have to take expectation value of J square, that is nothing but J into J plus 1. Then L square means expectation value of L square will be L into L plus 1. And then expectation value of S square, that is nothing but S into S plus 1. And we'll have H cross S square, that will be common from each term, divided by 2. You can see here, both state having same L value, and proton is spin half particle, right? So this term will be same. So, and also it is given that ESO is nothing but CL dot S. So unperturbed energy, this will be same, but ESO that is given CL dot S, C is some constant that you are going to find L dot S. So both states having same L and S. D means L equals to 2 and S spin is half here because proton is spin half particle. But this two state will have different ESO or spin orbit energy because of different J, right? Different J here. We'll get different energy for both state. Okay, so now we are going to find that. So basically, that's energy splitting. If you take that delta E is the energy difference between these two states that we can calculate actually. So how you can calculate that? So delta E, that will be nothing but ESO for J equals to 5/2 minus ESO for J equals to 3/2. And both state is having same L and S. So that difference will be arising because of what? So ESO you can write like CL dot S, CL dot S for J equals to 5/2 minus C expectation value of L dot S for J equals to 3/2. Okay. And this will be how much? So C will be common. And from here you will get when J equals to 5/2, J into J plus 1, that will be 5/2 into 7/2 minus L is J is 3/2, so J into J plus 1, that will be 5/2 into 3/2. Okay. So that will be basically C times 20/8. So that will be C into, we cancel with 4. So this will be 5, this will be 2. So that will be C into 5/2. And that energy difference is given. So delta E that we have obtained, that is C times 5/2. And that is given as 4 mega electron volt. Because the energy carried out by this gamma ray will be nothing but the energy separation between these two states. It means basically C will be how much? It will be 2 into 4, that will be 8 divided by 5 mega electron volt. That will be equal to 1.6 mega electron volt. So they ask you to calculate in terms of mega electron volt, that will be 1.6 mega electron volt. Okay. So, but you can do this kind of problem without solving anything that we are going to we used to teach in class. That if you have a spin orbit, if you take that spin orbit coupling into consideration, then the separation between these two states having same L value, separation between these two states having same L value will only be depends upon this higher J. So if you have a spin orbit Hamiltonian like HSO is something A into L dot S, L dot S, then the spin orbit will be depends upon, for the same L, that spin orbit you will get, here you will get A into a higher J. So you have higher J is how much here? 5/2. So A into 5/2 H cross square. If you have a state like P half and P3/2, then that energy separation between these two states will be A into 3/2 H cross square. So short trick you can use, just you have to take that constant into higher J1. That will be the separation between these two states, and you can proceed. And this is the way that we are getting, how we are getting that higher J that we have calculated.